Hi friends, welcome back to my YouTube channel. So today I am going to discuss about error control. So this is from the module 2 computer communication EC 407 from KTU syllabus. So basically I am discussing all the topics from the KTU syllabus related to computer communication course. So you can refer the previous videos and all the videos that I have discussed yet now. So you will get an idea so how far we are now. So previously we have discussed about flow controller and the protocols that we use to control the flow, and now we need to discuss about the error control. So error control, basically what we are doing, we need to find the error. So error detection and error correction is there. So we can go into the video and go into more details about error control. So basically we are going to discuss about the introduction part of the error control. So data communication requires at least two devices working together, one to send and another device to receive. So even such a basic arrangement requires a great level of coordination for ineligible exchange to occur. So basically as we discussed, like for a device to connect together, they should have one sender and receiver, and there must be a great deal of coordination between these two devices. So the most important responsibility of data link layer, flow controller and error control. So already I said that we have already discussed about flow control, so you can refer the previous videos. Like I have 2 or 3 videos regarding flow controller, and every protocol I have discussed detailed manner, so you can refer that. So now we are going to discuss about error control. So error control is the network must be able to transfer data from one device to another with acceptable accuracy. So for most application, a system must generate or guarantee that the data received are identical to the data transmitter. So this is the most important criteria, that what we send from sender to receiver, the receiver must receive the data same as the sender sent. So that is the criteria. So anytime data are transmitted from one node to next, they can become corrected in passage. So in the passage, like when we are sending the data from sender to receiver, there must be a link, there must be a connection. So in that way it can be corrupted. So the data can be corrected in the passage. So many factors can alter one or more bits of a message. So some application requires a mechanism for detecting and correcting errors. So some application can tolerate a small level error. For example, so random errors in audio or video transmission may be tolerable, but when we transfer text, we expect a very high level of accuracy. So let us discuss some issues related directly or indirectly to error detection and error correction. So all around, so we get an idea of error control. What is error control? So data can be corrected during transmission. Some application requires that error to be detected and corrected. So basically we are doing detection of the error and correction of the error. That is what we meant by error control. So types of errors. So first of all, we need to look into the type of errors. So whenever a bit flow from one point to another, they are subject to unpredictable changes because of these interference. So these interference can change the shape of the signal in a form. In a single bit error, a 0 is changed to 1 or 1 is changed to a 0. So that is the single bit error. And in a burst error, multiple bits are changed. For example, a 1 by 100 burst of impulse noise on a transmission. So for example, a 1 by 100 burst of impulse of transmission with the data rate of 1200 bits per second might change all or some of the 12 bits of information. So burst error means multiple bits can be changed. So single bit error means one bit can be changed. So 0 will change to 1 or 1 will change to 0. So these are the two types of error. So we can go more into the errors. So single bit error. The term single bit error means that only one bit of a given data unit, such as a byte or character or packet, is changed from 1 to 0 or 0 to 1. So the figure shows the exactly what I talked now. So sent bit is 000010, and the corrected bit is 00001010. So 0 is changed from 0 to 1. There is a change from 0 to 1. So that is the single bit error. So figure A shows the effect of the single bit error on a data unit. To understand the impact of the change, imagine that each group of 8 bits is an ASCII character with a 0 bit added to the left. So in figure 000010 was changed, meaning start of this text, but 001010 was received, meaning line feed. So single bit errors are the least likely type of errors in a serial transmission. So these errors we can see in serial data transmission. To understand why, imagine data sent at 1 MB per second. This means that each bit lasts only 1 by 10 lakh seconds or 1 microsecond. To understand why, imagine the data sent at 1 MB per second. So, for example, the bit error to occur, the noise must have a duration of only 1 microsecond, which is very rare. So, noise normally lasts much longer than this. So, we have discussed about single bit error now. So, next we are going to discuss about base error. So, base error means, the term base error means that 2 or more bits in the data unit have changed from 1 to 0 or 0 to 1. So figure B shows the base error example. So there you can see the send data and there is a lot of change corrected bits in the received data. So note that the base error does not necessarily means that the error occur in consecutive bits. So that is one thing. So the error cannot be, we cannot say that necessarily occur that the error should occur in consecutive bit. The length of the burst is measured from the first corrupted bit to last corrupted bit. So how we are taking the length of the burst error? So from the first corrupted bit to last corrupted bit. So some bits in between may not have been corrected. So a base error is most likely to occur than a single bit error. So the duration of noise is normally longer than the duration of one bit, which means that when noise affects data, it affects a set of bits. So number of bits affected depends on the data rate and duration of noise. For example, if we are sending a data at 1 kb per second, a noise of 1 by 100 second can affect 10 bits. If we are sending a data at 1 MB per second, the same noise can affect 10,000 bits. So this is all about base error. So redundancy means the central concept of detecting or correcting errors is redundancy. To be able to detect or correct errors, we need to send some extra bits with our data. So these redundant bits are added by the sender and removed by the receiver, and their presence allows the receiver to detect or correct corrupted bit. Detection versus correction. So we already said like the error control is basically two characteristics. So like detection and correction, error detection and error correction. So now we are discussing about the comparison between detection and correction. So the error correction, the correction of errors is more difficult than the detection. So in error detection, we are looking only to see if any error has occurred. The answer is simply yes or no. We are not even interested in the number of errors. A single bit errors is the same for us as a base error. In error correction, we need to know exact number of bits that are corrupted and more importantly their location in the message. So that's why we are saying error correction is more difficult than the detection. So the number of the errors and the size of the message are important factors. So if we need to correct one single error in an 8-bit data unit, we need to consider 8 possible errors location. If we need to correct 2 errors in a data unit at the same time, we need to consider 28 possibilities. So 2 raised to 8 possibilities, right? The data is misinterpreted, that is 2 raised to 8 possibility. Okay, so you can imagine the receiver's difficulty in finding 10 errors in a data unit of 100,000 bits. So that is why the detection is very easy comparable to correction. So forward error correction versus retransmission. So there are two main methods of error correction. So forward error correction is the process in which the receiver tries to guess the message by using redundant bits. So this is possible, as we see later, if the number of errors is small. So if the number of errors is small, we can go for forward error correction. So this is a process that the receiver tries to guess the message by using redundant bits. Correction by transmission is a technique which the user detect the occurrence of an error and asks sender to resend the message. The resending is repeated until a message arrives that the receiver believes is error free. Usually not all errors can be detected. So there are two methods that we are following: forward error correction and versus retransmission. And coding. So redundancy is achieved through various coding schemes. So the sender adds redundant bits through a process that creates a relationship between the redundant bits and the actual data bits. So we are adding redundant bits to the actual data. So there is a relationship between these two. And the receiver checks the relationship between the two sets of bits to detect the correct one and the errors. So the ratio of redundant bit to the data bits and the robustness of the process are important factors in coding scheme. So figure shows the general idea of coding. So we can divide the coding scheme into two broad categories. One is block coding and another one is convolution coding. So convolution coding is more complex. So here we can see there is a sender and receiver encoder, and sender is the encoder and receiver is the decoder. So message generator and message and redundancy. So in the sender side they will add redundancy bits to the message and they will send to the receiver, and receiver receive the information and they also remove the redundant bits, and checker function is there, and correct or discard. It will check for correct, it is correct or not, and then it will decode the message from the sender. So that is happening in the error control. So modular arithmetic. So this is the one of the approach that we are using in error control or error correction or error detection. So you will see this in the most of the places. Modular arithmetic. So before we finish this section, let us briefly discuss a concept of basic computer science in general, and error detection and error correction is particularly modular arithmetic. So our intent is here to delve deeply into the mathematics of the topic. We just represent just to information to provide background of material discussed in the section. So in the modular arithmetic, we use only a limited range of integer. We define an upper limit called modulus n. So when we use only integers 0 to n minus 1 inclusive, this is modulo n arithmetic. So this is called modulo n arithmetic. For example, if the modulus is 12, we use only the integers 0 to 11 inclusive. And for example, the modular arithmetics is our clock system. So it is based on modulo 2 arithmetic, substituting the number 12 to 0. And in a modulo n system, if the clock system is modular arithmetic, that's why we are saying like we are substituting the numbers from 0 to 12. So in modulo n system, if a number is greater than n, it is divided by n and the remainder is the result. So if it is negative, as many n's as needed are added to make it positive. Consider our clock system. Okay, if we start a job at 11 a.m. and the job takes 5 hours, we can say that the job can be finished by 6 p.m. 16 p.m. So if we are in the military, or we can say that it will be finished by 4 p.m. So the remainder of this 16 by 12 is 4. So addition and subtraction is a modulo arithmetic as symbol. So there is no carry when we add 2 digits in a column. So there is no carry when you subtract 1 digit from another in a column. So modulo 2 arithmetic. So we have discussed modulo n arithmetic. Now we are going to discuss about modulo 2 arithmetic. The only thing is that if the bits are same, then the resultant will be 0. If the bits are different, then the resultant is 1. So if we see here, 0 plus 0, it will be 1, and 0 plus 1, it will be 1. 0 plus 0, it is equal to 0, and 0 plus 1, it is 1, and 1 plus 0, it is 1, and 1 plus 1, it is 0. So there is no carry here. So it is like we can say that it is same bits. We will get 0, and different bits we will get 1. So in subtraction also the same format follows. So notice particularly that addition and subtractions give the same result. In this arithmetic we use the XOR, exclusive OR operation, for both addition and subtraction, and the resultant of the XOR operation is 0 if the two bits are the same. The resultant is 1 if two bits are different. So that is the thing about modulo arithmetic. So next we are going to discuss about block coding. So in the block coding we divide our message into blocks, each of k bits called data word. So the message is divided into blocks that of k bits called data word, and we add r redundant bits to each block to make the length n equal to k plus r, and the resulting n bit blocks are called code words. So n equal to k plus r, and k is the data word, and n blocks are called code word. So the resulting with k bits we can create a combination of 2 raised to k data word. With n bits we can create a combination of 2 raised to n code words. Since n greater than k, the number of possible code words is larger than the number of possible data words. So that is the thing, and the block coding process is 1 to 1. The same data word is always encoded as the same code word. So this means we have 2 raised to n minus 2 raised to k code words that are not used. So we call these code words are invalid or illegal. So figure shows the illustrations. So k bits data word, so that means 2 raised to k data words of k bits, and 2 raised to n code words, that is n bits. N bits means k plus r, and we are adding r redundant bits to the k bits, that is called code word. So 2 raised to k of them are valid, and 2 raised to k of them are valid, and 2 raised to n minus 2 raised to k code words are invalid or illegal code words. For example, in this coding scheme, k equal to 4 and n equal to 5, as we saw, we have 2 raised to 4 equal to 16 data words, and 2 raised to 5 equal to 32 code words. So we saw that 16 out of 32 code words are used for message transfer, and the rest are either used for other purpose or unused. So first we need to go through the error detection part. So we have one figure. So if you see here, the sender and receiver is there, k bit data words and n bit code words, then in the encoder side, and there is a generator function, and it is transmitted to the receiver there is a decoder. The code word is n bit is transmitted from sender to receiver, and there is a checker function. It will discard and extract the data word from the code word of k bits. So how the errors can be detected by using block coding? If the following two conditions are met, the receiver can detect the change in the original code word. So first one is the receiver has or can find a list of valid code words. That is the first condition. And the second condition is the original code word has changed to an invalid one. So figure shows the role of block coding in error correction. The sender creates a code words, the data words used by the generator that applies rules and procedure for encoding. Each code word sent to the receiver may change during transmission. If the received code word is the same as if the received code word is the same as one of the valid code words, the code word is accepted. The corresponding data word is extracted for use. If the code word received is not valid, it is discarded. However, if the code word is corrupted during transmission but the received word still matches the valid code word, the error remains undetected. So this is the error correction figure and its explanation. And this type of coding can detect only single error. Two or more errors may remain undetected. For example, let us assume that k equal to 2 and n equal to 3. Table shows a list of data words and code words. We will see how to derive the code word from the data word. So each data word have code words. So assume the sender encodes the data word 01 as 011 and sends it to the receiver. Consider the following cases. The receiver receives 011, it is a valid code word, and the receiver extracts the data word 01 from it. The code word is corrupted during transmission and 111 is received, the leftmost bit is corrupted, and this is not valid code word and it is discarded. So the code word is corrupted during transmission and 000 is received. The rightmost bit, 2 bits are corrupted. So this is valid code word since the receiver incorrectly extract the data word 00. 2 corrupted bits have made the error undetectable. Since 00 have the code word is 000, so it will detect it as valid code word, valid data word, and the 2 bits are remains undetectable. So an error detecting code can detect only the types of errors for which it is designed, or the types of errors may remain undetected. So these are all about this related to error detection part. So as I said, error detection is very simple comparable to error correction. So I think we discussed almost all topic related to error detection, and also the introduction for the error control part. So next our section will be mostly focus on the error correction part, and the next video you will probably get on today or tomorrow. So I think you can refer that. This is not a single topic. We have 1 or 2 videos other than this related to error control. So please share, please subscribe my channel if you like this video and for the following videos, and like, share and comment. Thank you for watching. If you like this video, please subscribe. So see you in the next video. Thank you.